Combinational circuits are fully specified by truth tables. However, when we design a sequential circuit, we need a state table for its specification. So we'll need to make sure that we obtain a state table or state diagram when creating a sequential circuit. We'll also need to choose the flip-flops and find a combinational circuit structure in order to create a circuit that fulfills the stated specifications. The number of flip-flops needed is determined by the number of states in the circuit. In particular, n flip-flops can represent up to 2 to the n binary states. We derive the combinational circuit from the state table by finding the flip-flop input equations and the output equation. Once we know the type and number of flip-flops and assign binary combinations to the states, we can treat the process as a combinational circuit problem, which is something we already know how to do. Here we see the procedure for the design of sequential circuits. You'll notice this is pretty similar to design procedures we talked about in modules 1 and 3. Take a minute to review the steps in the procedure, and then we'll move on to finding state diagrams and state tables. We usually begin with the verbal description and interpret it to find a state diagram or state table. As stated in the companion text, this is a creative part of the process. State is used to remember something about the history of input combinations applied to the circuit. In some cases, the states may literally store input variables, retaining a complete history of the sequence appearing on the inputs. In most cases, however, a state is an abstraction of the sequence of input combinations at the triggering points. In formulating a state diagram or state table, we need to write down the abstraction represented by each state. Sometimes we describe the abstraction by referring to values that have occurred on the outputs as well as on the inputs. As we formulate a state table or state diagram, we add new states, but we don't want to add too many. Instead of adding a new state for every current state and possible applied input combination, we try to reuse states to prevent uncontrolled state growth. When the power in a digital system is first turned on, the state of the flip-flops is unknown. In order to keep things simple, the circuits we design have to have an unknown initial state, and the hardware mechanism to put them in that state, which is called a global reset signal. We assume that this signal gets activated on power up. The initial state is often referred to as the reset state. The reset can be asynchronous and take place without clock triggering. In this case, the reset is applied to the direct inputs on the circuit flip-flops. Design here assigns 0 to the initial state of the flip-flops to be reset. We should keep the asynchronous aspect separate from the synchronous design. Alternatively, the reset may be synchronous and require a clock triggering event to occur. Here we incorporate the reset into the synchronous design of the circuit. A simple approach to synchronous reset for D flip-flops, without formally including the reset bit in the input combinations, is to add the AND gate, as shown in this figure, during the normal circuit design. The book has 2 examples to illustrate the formulation process. One is the sequence recognizer, while the other is the BCD to XS3 decoder. We'll cover the sequence recognizer here, but I encourage you to take a look at example 4.4 in the text. Here we examine a circuit that recognizes the occurrence of a particular sequence of bits, regardless of where it occurs in a longer sequence. The sequence recognizer has one input X and one output Z. It has a reset applied to the direct reset inputs on its flip-flops to initialize the state of the circuit to all zeros. The circuit is to recognize the occurrence of the sequence of bits 1101 on X by making Z equal to 1 when the previous 3 inputs of the circuit were 110 and the current input is 1. The first step in the formulation process is to determine whether a state diagram or state table must be a Mealy or Moore model circuit. The portion of the preceding specification says making Z equal to 1 when the previous 3 inputs of the circuit are 110 and the current input is 1 implies the output is determined from not only the current state, but also from the current input. So we need a Mealy model circuit with the output dependent on both state and inputs. For the sequence 1101 to be able to produce output value of 1 on the final 1, the circuit must be in a state that remembers the previous 3 inputs were 110. We start by defining an arbitrary initial state A as the reset state. If a 1 occurs from the input, since 1 is the first bit in the sequence, the event must be remembered. So a second state B is used to establish this representation of the first 1 occurring. Since this is not the final 1 in the sequence, the output is 0. The next bit of the sequence is 1. When this 1 occurs in state B, a new state is needed to represent the occurrence of 2 1s in a row on the input. That is the occurrence of an additional 1 while in state B. So we add a transition and a new state, C. The next bit of the sequence is a 0. When this 0 occurs in state C, a state is needed to represent the occurrence of 2 1s in a row followed by a 0. So the additional state D with the transition having a 0 input and a 0 output is added. Since state D represents the occurrence of 110 as the previous 3 input values of X, the occurrence of 1 in state D completes the sequence to be recognized. So the transition for the input value 1 from state D has an output value of 1. So we fill in the remaining state transitions based on the idea that the recognizer is to identify the sequence 1101 regardless of where it occurs in the longer sequence. So we fill in the remaining states and we obtain this diagram. From the state diagram we can derive the state table. One final issue is whether we used any excess states in the diagram or table. In this case, we were pretty lucky and didn't have any excess states. There are formal ways of minimizing excess states. The textbook from Katz entitled Contemporary Logic Design from Prentice Hall covers how to do this if you're interested in learning more about this subject. The states in the example were assigned symbolic names rather than binary codes. It's necessary to replace these symbolic names with binary codes in order to proceed with the design. In general, if there are m states, the codes must contain at least m bits, where 2 to the n is greater than m. And each state must be assigned to unique codes. So for our circuit, we would need at least 2 bits. The first state assignment method we'll consider is to assign codes with m bits in counting order. For example, the states A, B, C, and D can correspond to the codes 0, 0, 0, 1, 1, 0, and 1, 1. An alternative that is attractive, particularly for using K-maps for optimization, is to assign the codes in gray code order, with codes 0, 0, 0, 1, 1, 1, and 1, 0. There are a number of specialized state assignment methods. The most popular of these methods is one flip-flop per state, or the one-hot assignment. Here we use a distinct flip-flop for each of the m states, so it generates codes that are m bits long. Each valid state contains m bits, with one bit being equal to 1 and all the others 0. You can think of going from one state to another as passing a token, the single one from the source state to the destination state. Since each state is represented by a single one, logic for entering a particular state is totally separate from logic for entering other states. In the companion presentation, we'll see how to use the sequentially assigned gray code and one hot code for the sequence recognizer design. Thanks so much for watching. Be sure to check out the companion